Here we have the balanced equation for the decomposition of nitrogen dioxide into nitric oxide and oxygen. In part A, they want us to use the data to show that the decomposition of nitrogen dioxide is a second-order reaction. So over here we have the time, and we also have the concentration of NO2. To show this is a second-order reaction, we need to remember the integrated rate law from the previous video. So we found that 1 over the concentration of A is equal to the rate constant K times the time plus 1 over the initial concentration of A. So that's the integrated rate law for a second-order reaction. For our reaction, A is equal to NO2, so we can plug that in. So now we have 1 over the concentration of NO2 is equal to the rate constant K times the time plus 1 over the initial concentration of NO2. And this is in the form of Y is equal to mx plus B. So in the previous video, we talked about if you put time on the x-axis and 1 over the concentration of NO2 on the y-axis, if the reaction is second order, you're going to get a straight line. And the slope of that straight line, m, is equal to the rate constant k. And the y-intercept is equal to the initial 1 over the initial concentration of NO2. So if we're going to show that this is a second order reaction, we already have the time, but we have the concentration of NO2. We need 1 over the concentration of NO2. So let's plug that in here. So we need to get 1 over the concentration of NO2. And so that would be molar to the negative first. So let's go ahead and do that. Here's the concentration of NO2. So we need to take 1 over 0.008. So we get out the calculator and we take 1 divided by 0.008 and we get 125. So this is 125. Next, we have 1 over 0.0066. So 1 divided by 0.0066 gives us 152. So we have 152 here. Next, 1 over, so we have 1 over 0.0056, and that gives us 179. So rounding to 179. And then finally, we have our last one, which is 1 divided by 0.00485. And we get 206. So we have 206. And so we know this is going to go on our y-axis, right? And time is going to go on our x-axis. So let's look at the graph here. All right, and let's find some of our points. So we have time on our x-axis, and we have 1 over the concentration of NO2 on the y-axis. Our first point would be when time is equal to 0, y is equal to 125. So when time is equal to 0, 125 is right about there. So that's our first point. Our next point would be time is equal to 50, y is equal to 152. So when time is equal to 50, right, 152 would be pretty close to there. All right, next we have time is equal to 100, y is equal to 179. So when the time is equal to 100, 179 would be somewhere about there. And then finally, our last point, when time is equal to 150, y is equal to 206. So when we're talking about 150, right, 206 should be somewhere in there. And let's see if we have a straight line. So let's go ahead and draw a line in here. All right, and we can see that these points are pretty much on a straight line. All right, so we've shown that this is a second order reaction. Obviously I didn't do a perfect job of graphing, but you can see that these points are on our straight line. And we know the slope of this line, right? The slope is equal to the rate constant K. So we're done with A, right? We've taken our data and we've shown that we get a straight line when we put time on the x-axis and 1 over the concentration of NO2 on the y-axis. So we're done with A. Move on to B, where we're trying to figure out the value of the rate constant. And this reaction was at 300 degrees C. So all we have to do is find the slope of our line, and we'll find our rate constant. So of course, one way to find the slope would be to take delta y over delta x, right? So the slope is equal to the change in y over the change in x. And so you could find a point here and a point here, right, on your line, and you could find the slope that way, right? So that's one way to do it. This would be the change in y, and this would be the change in x. And the units, right, for y we have molar to the negative first, so molar to the negative first, and for the x we have seconds. So the unit would be, I could rewrite this as 1 over molar times seconds. Right, so that's our unit for our second order reaction. We could have also figured out our unit using the rate law. Rate is equal to the rate constant K times the concentration of, we had NO2, and since this is a second order reaction, this would be squared. So rate would be molar per second, right? And then we have the rate constant K times the concentration squared. So this would be molar squared. Right? So let's go down and get a little bit more room. So this would be molar over seconds is equal to K times molar squared. One of those molars would cancel. Right? So now we have 1 over seconds is equal to K times molar, and so once again we find that K is equal to 1 over molar times seconds. So it doesn't matter how you get your units here. We know that's going to be the units for K. We could find it out by looking at those 2 points that I marked on our graph, but to get an exact answer, let's use our calculator. So let's take out our calculator and let's plug everything in. Right, so let's go to Stat, and we'll go to Edit here, and we'll go ahead and plug in our points. So when x is equal to 0, y is equal to 125. When x is equal to 50, y is equal to 152. And let's see, next when x is equal to 100, y is equal to 179. And then finally, we have when time is equal to 150 seconds, right, y is equal to 206. So we have our points in there now, and we can go back to Stat, and we can hit Calc, so F1 right here, and we can hit Enter twice, and then we can do a linear regression, right, which should be right here for F2. And when we do our linear regression, we find that B, right, on our calculator here, B is the slope. Right, so B is equal to 0.54, so that's the slope of our line, and therefore that's the value of our rate constant. Right, so K, or our rate constant, is equal to 0.54, and this was 1 over molar times seconds. So we have figured out the value for K, right, using the data that was given to us.